In this lesson, we will study partial fractions. Now, the sums of rational expressions are found by combining two or more, right, expressions, like adding two expressions together or subtracting one from the other in order to get a sum. So in this lesson, we are reversing that process. So we are given one rational expression and we are going to be asked to rewrite it or express it as a sum of two or more rational expressions. So what we must understand is a special type of sum of rational expressions is called the partial fraction decomposition. Each term in the sum is a partial fraction. Here's an example of what I'm referring to. So we have experience taking these two expressions here on the left and adding them together, or, even subtracting one from the other. And so we have experience combining these two, if you will, and getting this sum here. In this lesson, we are given a sum like this on the right-hand side, and actually we are being asked to go in this direction. Okay, is given a sum like this, given a single rational expression, to rewrite it as a sum of terms. Okay, and this here would be considered the partial fraction decomposition. Each one of these is a partial fraction, so this is a partial fraction. Here's another partial fraction, but altogether this is the partial fraction decomposition for this expression here. So for every example we look at, we'll be given an expression like this, and we will be asked to find the partial fraction decomposition for each of these expressions, okay? Now here are some steps to follow. I know it's a lot of writing. I know it sounds pretty abstract, but at least just write them down, add them to your notes, and I will be walking you through this process for each of these examples. So we must first begin with a proper fraction. Remember that a proper fraction is a fraction whose numerator is of lesser degree than the denominator. If we do not have a proper fraction, I'm going to show you eventually that what we're going to have to do is divide. Most likely use long division to rewrite the fraction so that it is a proper fraction. So if it's not a proper fraction already, you have to use long division to get it to be a proper fraction. Number two, or step two, you want to factor the denominator completely. Completely factor the denominator. Step three, if you have a linear factor, ax plus b, the decomposition must include the term a over ax plus b. Now, this a here, this capital A here, represents a constant. You're going to have to figure out what that constant needs to be. And that's the quest. That's the challenge, right? That's the work you and I will be doing, is figuring out what this numerator needs to be. But it will be of this form, some constant a over this linear factor ax plus b. If you have a repeated linear factor, ax plus b raised to the power of some integer m, then the decomposition must include the terms a sub 1 over the linear factor ax plus b plus a sub 2 over the linear factor ax plus b raised to the second power plus, and then etc. until you get to a sub m over the factor ax plus b raised to the power of m. So a few things here. Each of these numerators are different. So this is a constant a sub 1. The next numerator, a sub 2, is a different constant. Another thing that you want to recognize is that the first denominator is ax plus b raised to the first power. The second denominator is ax plus b raised to the second power. The third denominator, which we don't see here, will be ax plus b raised to the third power, and then to the fourth power, then to the fifth power, and so forth until you have it to the mth power. If you have, I miswrote here, for each, not district quadratic factor, but each distinct, you may want to change your notes here. For each distinct quadratic factor, cx squared plus dx plus e. That's a quadratic factor. The decomposition must include the term, now watch this, bx plus c over that quadratic factor. So notice that this numerator is degree 1, where the degree of the denominator is degree 2. That was true in step 3 up here, right? This is just a constant, a sub 1. So that's degree 0 over degree 1, because that's linear. Degree 0 over degree 1, right? Partial, again, a proper fraction. Here we have degree 1 over degree 2, again, a proper fraction. If your quadratic factor is a repeated quadratic factor, then the decomposition must include the terms. Now you have a linear factor as the numerator over the quadratic factor, a linear factor again over the quadratic factor, but notice that this time it's raised to the power of 2, and the next denominator will be the quadratic factor raised to the power of 3, and then to the power of 4, and so forth until you have it raised to the power of n, right, to the power of n, okay? So notice that each of these numerators, you're going to have to figure out what these are, and that's the work that you and I have to do in partial fraction decomposition. You're going to have to figure out what b sub 1 is, what c sub 1 is, what b sub 2 is, what c sub 2 is. So you and I are basically looking for what are these constants, what are these coefficients, all right? And then finally, step 5, we're going to use algebraic techniques to solve for the constants in the numerators of the decomposition. That's kind of like what I just said. So for now, just write down these steps, if you will, and I'm going to explain to you as we go. All right, here we go. Let's jump into this. All right, here's our first example. Find the partial fraction decomposition of this expression. Now, a few things I want you to notice. Number 1, this expression, this fraction, let's just call it a fraction, is a proper fraction. Notice that the degree of the numerator is 1, and the degree of the denominator, if you were to FOIL this out or distribute this out, x times x is x squared, so the degree of the denominator is 2. So you got degree 1 over degree 2. So this is definitely proper. Let's move down now to step number 2. Step number 2 says to completely factor the denominator. Good news, this is done for you. And it won't always be done, but for this first example, it's done. This denominator is already factored. So step 3, we do have a pair of distinct linear factors here. So we know, and if I can get this started here, we know that this must be equal to, right, some constant, let's call it a, over the first linear factor, plus some other constant, let's call it b, over the other linear factor. So this is the form of the partial fraction decomposition. This first fraction is called a partial fraction. Here's another partial fraction. So what you and I need to do right now is we need to find what is a, what's this constant a, and what is this constant b, such that when I add these two expressions together, I get this original expression. So step number 5 says use algebraic techniques to solve for these constants, a and b in the numerator, in the numerators. So this is what I'm going to do. I'm going to multiply both sides of this statement, both sides of this equation, by the LCD. Now, the LCD will be the product x plus 1 times x plus 2. So I'm basically going to multiply both sides by this complete denominator. Now, please excuse, this is a little sloppy, so please excuse that, but I'll clean this up in just a second. So I'm multiplying both sides by the LCD. Now, notice, please, that, this product divides out with that product, completely, right? And over here on the right side, x plus 1 divides out with x plus 1, and x plus 2 divides out with x plus 2. So now let me rewrite what we have. So now we're left with this statement or this equation. It's actually really an identity. Negative x is equal to a times x plus 2 plus b times x plus 1. Now don't forget, we're trying to figure out what is a and what is b. Now, this statement here must be true for all values of x. So this is what I'm thinking. If I can plug in a value for x in a clever way such that this whole term gets canceled out, I'll be left with just a in this equation, and then I can solve for a, right? So what can I substitute in for x here in order for this whole term to cancel? Well, if x is -1, notice that you would have -1 plus 1, which is 0, and 0 times b is 0, and this whole term goes to 0. It cancels out, if you will. So what I'm going to do is I'm going to plug in x equal to -1 so that this whole term goes away, and then I can solve for a. All right, notice that I've let x be -1. Remember, you have to plug in x equal to -1 whenever x appears in the identity. So you're letting this x be -1, and this minus -1 just becomes +1. When you let x be -1 here, this just is +1, so 1a, or just a, if you will. And when you let x be -1 here, this is what gives you the 0. So b times 0 just goes away. And notice that this whole identity gives you a must be 1. So there, we already have it. We have one of our constant, that is, a must be 1. All right, now what I want to do next is go back to this statement. You know, this one here is so important. I'll be coming back and forth to this statement. Okay, so what we just finished doing is plugging in -1 for x in order to eliminate b and solve for a. Now let's turn that around. Let's come back to the statement again, but this time let's try to eliminate a so that I can solve for b. So what would you and I plug in for x here in order for a to cancel? In other words, what value do you add to 2 in order for this to be a 0? If you said -2, that's exactly what I'm going to do. I'm going to let x be -2 because -2 plus 2 is 0, and 0 times a will be 0, and so this whole term gets canceled. So I'm going to do this process again, but this time we're letting x be -2 so that we can cancel a and then solve for b. So here I've substituted -2 in for x. Remember to plug -2 into every single time where you see an x. And now it's time to solve for a. Excuse me, solve for b. A is being canceled, right? So right here you have a times 0, so that's just 0. And here we are left with plus b times -1. So that's going to give us 2 is equal to a times 0 is 0, so that's gone, is equal to -b. So this gives us, if I could just put implies here, b must be -2. So you and I have done it. We are ready to write down the partial fraction decomposition for our expression. We have a and we have b. And there we have it, folks. This here is the partial fraction decomposition for this fraction. All right. And again, if you wanted to, how do we check our work? How do we verify that we're right? Well, you and I already know from previous studies in algebra how to go from this sum here to this fraction. So find the common denominator, which is just x plus 1 times x plus 2, and actually do that algebra, add these two expressions, and you should get this expression on the left. Okay. So just to recap, they gave us this expression. You and I found the partial fraction decomposition. All right, so good job. Let's look at another example. All right, example 2 here. Find the partial fraction decomposition of 2x to the 4th power minus 8x squared plus 5x minus 2 divided by x cubed minus 4x. The first thing I want you to notice is that this is not a proper fraction because the numerator is degree 4, the denominator is degree 3, so this is an improper fraction. We must rewrite this so that it is proper. So what we must do is divide. we're going to divide the numerator by the denominator. We're going to set this up using long division. All right, I set up the long division here. I'm actually going to work this out with you. Just to make sure, I mean, I don't know how long it's been since you've done long division, so let's go ahead and just do this together, okay? So I think to myself, what do I multiply x cubed by in order to get 2x to the 4th power? Well, x cubed times 2x will give me 2x to the 4th power, so I'm going to write 2x up here. And now I will multiply each term of my divisor by 2x. And that'll give me 2x to the 4th power minus 8x squared. Okay, I will subtract this from my dividend. And notice that this gives you 0. So what I'll do is I'll go ahead and bring down the next terms in my dividend, which is 5x minus 2. We are done dividing here because this here is degree 1 and your divisor is degree 3. Whenever your remainder is of lesser degree than your divisor, you are done. Degree 1, degree 3. So what we just determined is that this expression that they gave us can be rewritten with this quotient and this remainder. Okay? So this is what we have. This is the original expression they gave us. We just divided and we got 2x, there's the quotient, plus the remainder, 5x minus 2, over the divisor, x cubed minus 4x. Now, so what you and I need to do at this point is do the partial fraction, or find the partial fraction decomposition, for this fraction here. We already have 2x, so that's good. That's going to follow us all the way to our final answer. But now you and I need to find the partial fraction decomposition for this proper fraction. All right, I just took that fraction and I have it here. We will not forget to bring that 2x, you know, the quotient that we got a little while ago. We will not forget to write that in our final answer for the partial fraction decomposition. But for now, let's just focus on this fraction. Remember step 1, well, we did that. That was make sure the fraction is proper. So step 2 is to factor the denominator. So let's go ahead and do that now. So if I factor the denominator, I'll factor out the GCF of x, which gives us x squared minus 4. And it can be factored further, as x times x plus 2 times x minus 2. I'll put that there. So I have completely factored the denominator. All right. So notice that we have 3 distinct linear factors here. 3 distinct linear factors here. Okay? So what we will do is we will rewrite this. We know that this must be equal to, let's see. All right, we have our original expression here for the fraction, must be equal to a. Now notice this is a constant over the first linear factor, plus b over the second linear factor, and then plus c over the third linear factor. So you and I, for this example, must find all 3 constants, a, b, and c. All right, I'm going to use the same algebraic technique that I used in the previous example, which was to multiply both sides of this equation by the LCD. Notice that the LCD is basically this denominator here, which in factored form, by the way, guys, the factored form of this denominator is x times x plus 2 times x minus 2. So I'm going to multiply the left-hand side and the right-hand side, each term of the right-hand side, by the LCD, which is basically this denominator here. All right, I multiplied both sides by the LCD, and I got the following identity. 5x minus 2 is equal to a times x plus 2 times x minus 2, plus b times x minus 2, plus c times x plus 2. Now remember that this is an identity, right? This is an identity, and it must hold true for all values, right? for all values of x. I'm highlighting it just because I might come back to this often. The previous statement is also an identity. It holds for all values of x as well, except for x equal to 0, x equal to -2, and x equal to +2, because at that point, you would get something undefined, right? But this statement here is an identity that holds true for all values of x. So I want to use something similar to what I did earlier, and that is start plugging in values for x in order to start finding what a, b, and c are. So what I notice right now is that if I, let's see, if I plug in x equal to 0, notice that this whole term will go away, and this whole term will go away, and then I can solve for a. Let's do that now. Let's plug in 0 for x. All right, I went ahead and did that. When I plug in 0 for x here, you're just left with -2. When you plug in 0 for x here and here, you're just left with 2 times -2, which is -4 times a. When you plug in 0 for x, this whole term will go to 0, and the same thing goes for this term. So you can see that, or we can see that a is positive 1/2. So we found a. We found our first constant. So now let's go back to our identity here and find b and c. In order to find b, I need a and c to cancel, both of them. I'm noticing that if I let x be -2, this will be -2 plus 2, which is 0, and this whole term will go away. If I let x be -2, this term also goes to 0 because -2 plus 2 is 0, right? So I'm going to go ahead and let x be -2. Let's plug in -2 for x. All right, I went ahead and plugged in -2 for x. 5 times -2 is -10, minus 2 is -12. Here, when you plug in -2 for x, you get this factor to be a 0, so that all goes to 0. Same is true over here. When you let x be -2, this factor here becomes 0, so the whole term is 0. When you let x be -2 here, you have -2 minus 2, which is -4, times -2, that's +8. So that's how I got the 8b. And we want to divide both sides by 8 to get b is equal to -3/2. So we found a, the constant a, and we found the constant b. Now, finally, let's solve for c. So now you want a and b to cancel. I'm noticing that if you let x be 2, both a and b will go to 0. Because 2 minus 2 is 0, 2 minus 2 is 0. So this time around, let's go to our identity and plug in x equal to +2, and then solve for c. All right, I hope you agree with me that when you let x be 2, you get 8 here on the left-hand side. 5 times 2 is 10, minus 2 is 8. This term goes to 0 because right here, 2 minus 2 is 0. This term also goes to 0 because 2 minus 2 is 0. And this term here turns out to be 2 plus 2, which is 4, times 2 is 8, so 8c. So I hope you see that c is equal to 1. All right, you guys, we are done. We just have to write down our final partial fraction decomposition. We have found a, b, and c. All right, I have the complete partial fraction decomposition here. Remember 2x, first of all, excuse me, this is the original expression. And then we used long division to get this quotient, 2x. And then this is what we just found. We found the first constant to be +1/2. We found the second constant to be equal to -3/2, and the third constant to be equal to 1. Now, I am asking you to not leave your answer like this, but to rewrite this so that you don't have these complex fractions, all right? So this can be rewritten as 1 over 2x. And then this next term can be rewritten. You know what? I'm going to go ahead and bring down the minus sign right here. And this can be rewritten as 3 over 2 times x plus 2. Like that. I think that's a lot neater. And then this one's fine. 1 over x minus 2. Okay? So here is the partial fraction, I'll box it, the partial fraction decomposition for that expression. Wasn't that a lot of fun? Oh my gosh. All right, let's look at another example. So far, the two examples that we've looked at have had distinct linear factors. The next example we look at, we will see repeated linear factors. All right, we are finding the partial fraction decomposition of 2x over x minus 1 cubed. Now notice that, first of all, this is a proper fraction. We got degree 1 over degree 3. Secondly, notice that this denominator is already factored, right? X minus 1 cubed is just x minus 1 times x minus 1 times x minus 1. Thirdly, notice that we are going to have a repeated linear factor. X minus 1 is linear, and then when you raise it to the third power, yes, it is cubic, which just means that you have a linear factor that's being repeated 3 times. So we're going to be able to rewrite this as a over the linear factor x minus 1. Now watch this, plus b over, watch this, x minus 1 squared, and then plus c over x minus 1 cubed. Now we stop there because this was degree 3, right? So once we get to degree 3 down here, then we're done. Had this been degree 4, we would have kept going until we got to degree 4, okay? So you and I need to find A, B, and C. All right, let's do the same strategy, the algebraic technique that we've been using the last couple of times, which is multiplying both sides of this identity by the LCD. The LCD is x minus 1 cubed. All right, so we did it. We went ahead and plugged in, or not plugged in, we multiplied both sides by the LCD. And we're left with 2x is equal to a times x minus 1 squared plus b times x minus 1 plus c. Notice that c is just a constant. If you and I were able to plug in something for x that allows a and b to go to 0, then we can solve for c. So let's go ahead and plug in x equal to 1. 1 will do it because 1 minus 1 is 0. 1 minus 1 is 0. So if we plug in x equal to 1, both a and b will cancel or go to 0, and we'll be left with c. So let's do that now. All right, so plugging in x equal to 1 leads us to c equal to 2. We already have one of our constants. That's awesome. Now all we need is a and b. Now what I'm going to do here is, because this is just a constant and we just found it, let's go ahead and update this identity with this c value now that we know what it is. So what you're going to see me do is rewrite this. Actually, it'll be easier for me just to erase it if you allow me to, and go ahead and plug in 2. We found c to be 2. So c is 2. All right, so here we go. What we want to do now is plug in a value here for x, okay? We must remember that this is an identity. So we're allowed to plug in whatever we want for x, whatever we want. So let's just plug in, something that's easy for us to arithmetically. So let's just plug in any x value you want. Choose an x value. What do you want to plug in? I suggest you don't plug in 10 because if you plugged in 10, although you could, it'd be 10 minus 1, which is 9. 9 squared is 81, right? And things just get too big. So let's stick to small values, if you will. So how about we plug in, how about x equal to 0? Let's plug in x equal to 0. This is an identity, so it should hold for all values of x. What do you get when you let x be 0? All right, when I let x be 0, I get 0 is equal to a minus b plus 2. That's awesome. This is an equation, linear equation, in just 2 variables. Let's plug in a second value for x here into this statement. Let's plug in, I don't know, how about -1? Let's plug in -1 and see what we get. When I plug in -1, I get the following. -2 is equal to 4a minus 2b plus 2. But we can simplify this a little bit. Let me go ahead and subtract 2 from both sides. And actually, I can rewrite this as -4 is equal to 4a minus 2b. Actually, I can do better than that. I just subtracted 2 from both sides, but I can divide everything by 2. If I divide everything by 2, I'll get negative 2 is equal to 2a minus b. So what we'll do at this point is we'll take this, let's see, we'll take this equation here, and we'll take this first one here, but let me actually subtract 2 from both sides. Let me do that really quickly for us. When you subtract 2 from both sides, you get negative 2 is equal to a minus b, right? So I'm going to take this equation here and create a system of equations and solve for a and b. All right, so notice that I have this system of equations now, and what I want to do is solve for a and b. I can solve for a and b. Let's see, if I multiply, I don't know, there's a lot of different things you could do. If you multiply this first equation by negative 1, that will isolate your a variable, right? And so you would get just a is equal to 0. Okay, so this would be a negative a plus 2a is positive 1a, and then negative 1 times negative b is positive b, minus b is 0, and then negative 1 times negative 2 is positive 2, and a negative 2 gives you 0. So we just found that a is 0. Awesome. Now that we know that a is 0, we can go ahead and plug in that value into, let's say, this statement here and solve for b. So this will give us 0 minus b is equal to negative 2. And that is to say negative b is equal to negative 2, or b is 2. All right, everybody, we have a equal to 0, b equal to 2, and we found c being 2 earlier. So we're able to write down our final answer. Let's do it. All right, so here's the partial fraction decomposition, but you and I already know that 0 divided by x minus 1 is just 0, so we're going to get rid of this term. We don't need it. But here's a, b, and c. So let me write down our final answer, that 2x over x minus 1 cubed, this is the original expression that they gave us, is simply equal to 2 over x minus 1 squared. If I could, that looks really sloppy. Hold on, sorry guys. X minus 1 squared, and then plus 2 times x minus 1 cubed. So here is the partial fraction decomposition. Again, this was an example of us having a repeated linear factor. What I want to do is end this lesson with a couple examples where you have quadratic factors, okay? This next example, example number 4, you will have a distinct quadratic and linear factor. So you'll have quadratic and a linear factor together. All right, we're finding the partial fraction decomposition of x squared plus 3x minus 1 over x plus 1 times x squared plus 2. Good news, this is proper. This is a proper fraction. We have degree 2 over degree 3 because x squared times x is x cubed. So it is proper. Let's move on to step number 2. Completely factor the denominator. Well, it already is. This is cannot be factored further, and neither can x squared plus 2. So we already have it factored. Step 3, let's break this up and follow how this will play out. All right. So here we have, notice that your first factor is linear. That means that the partial fraction decomposition must include the term a over x plus 1. Now, notice that this is a constant, so it's degree 0 over degree 1. But the next term here in the partial fraction decomposition, the denominator is going to be the quadratic factor this time, right? And because this is quadratic, this numerator must be linear, right? 1 less degree. So this will be bx plus c, all right? So we have degree 0 over degree 1, and degree 1 over degree 2, okay? Again, like always, we want to find a, b, and c. I'm going to use the same algebraic technique of multiplying both sides by the LCD. The LCD is basically this denominator here. All right, multiplying both sides by the LCD leaves me with just the numerator, like always, over here on the left side, x squared plus 3x minus 1. But on the right side, we have a times x squared plus 2 plus bx plus c times x plus 1. All right, so I mean, one thing that I noticed right away, everybody, I know I want to find a, b, and c. I noticed right away this factor here because I think to myself, if x were -1, then this would be -1 plus 1, which is 0, and this entire term would go away, would go to 0, and I would only be left with a to solve for. So that's exactly what I'm going to do. I'm going to let x be -1 so that all of this will go to 0, and then I'll solve for a. Okay, I let x be -1. When you let x be -1 here on the left-hand side, you do get -3 on the left-hand side. And when you let x be -1 for this entire term here, it goes to 0 because of this factor. And here, -1 squared, of course, is 1, plus 2 is 3, so that's 3a. So this gives us that a must be -1. All right, keep that handy. We have one of our constants. What I'm going to do now is something similar to what I did in the previous example. I'm going to go back to our identity, and I'm going to let I'm going to let a be -1 because that's exactly what it is. So a is -1. So I'm going to update my identity, if you will. I'm going to update it with this a value being -1. All right, now look at your identity. We know a is -1, so now we're looking for b and c. If I let x be 0, b times 0 would be 0. And then I would only be left with c, and I can solve for c. So let's do that now. Let's plug in x equal to 0. All right, I plugged in 0 for x. That means the only term you're left with on the left-hand side is -1. Of course, 0 squared is 0, plus 2 is 2, and 2 times -1 is -2. When you let x be 0, b times 0 is 0, so that's wiped out, and you're left with just c times 0 plus 1, which is 1. So it's just c. So here you can see that c then must be equal to +1. Now we know a is -1. Remember, this is a here, guys. A is -1. C is +1. Now all we need is b. What I'm going to do now is I'm going to plug in 1 for c to update my identity. Now we know c is 1. All right, so we found a to be -1, c to be +1. Now we just need b. We can plug in whatever we want for x and solve for b. Why? Because this is an identity. We can plug in whatever we want. So plug in something that's reasonable, something that makes it easy for you, right? So plug in whatever you want. So let's go ahead and don't plug in 0, because if you plug in 0, b times 0 is 0, and you wiped out b. We want to solve for b. So plug in something other than 0. How about you plug in, I don't know, let x be 1. Okay, plugging in 1 for x here on the left-hand side does give you 3. Plugging in 1 here gives you -3. Plugging in 1 here gives you b plus 1. And then plugging in here 1 here gives you a 2. Let's go ahead and solve for b now. All right, so you're going to get 0. Excuse me, you don't get 0, you actually get 6, right? Adding this 3, add +3 to the left-hand side gives you 6. And then I'm also going to distribute this 2 here. So you're going to get 2b plus 2. Cool. And that will leave you with 2b is equal to 4, which gives you that b is equal to 2. So we found b is 2, we found a is -1, and we found that c is +1. All right, so let's write out the partial fraction decomposition. All right, everybody, we did it. So here is a over x plus 1, and then we have b x plus c, right, over x squared plus 2. This is the partial fraction decomposition. What I would like to do now before we jump to our last example is I want to show you another way to find your constants when you have quadratic factors. So I want to look at this example one more time, not from scratch, but I want to go back to where we had an identity. And if I can, I want to show you, here was the identity here. But allow me to plug back in A here and C here, okay? All right, so this is the identity that you and I were working with just a minute ago. Now, there's another method that is many times actually way more convenient that I want to show you now, okay? So what we just finished doing, I mean, it works, but you're going to see in a lot of examples that the following method that I'm about to show you now is works out, and it's more convenient for a lot of the problems that we want to provide the partial fraction decomposition for. So what I'm going to show you to do with this example is I want you to actually distribute this out, right? So multiply that out and distribute the A. All right, I went ahead and did that. And now what I want you to do is I want you to combine like terms. So in other words, I want you to notice that ax squared and bx squared are like terms, right? So I want you to group them together. Notice that bx and cx are like terms, so I want you to group them together. And these constants, 2a and c, are like terms, so I want you to group them together. So this is the associative property of addition. All right, I went ahead and did it, and I could barely fit it, okay? So ax squared, so all of your squared terms have a coefficient. So this squared term here, let me underline it. So this squared term here and this squared term here. Notice the coefficients are a and b. So that's why I have a plus b and then x squared. Hey, after all, you can distribute the x squared and get those two terms right back, right, everybody? Other like terms here are either your first degree terms, bx and cx, and notice that the coefficients are b plus c. So that's why I have b plus c times x. Finally, what we have here is are the constant terms. So you got 2a, I don't know if I need to underline them, but I'll go ahead and do it, 2a and c, so 2a plus c over here. All right, the next thing that we will do is we will equate the coefficients, okay, and create a system of equations. So a system of equations is formed by equating the coefficients of like terms on each side of the partial fraction decomposition. So equating the coefficients of like powers of x, we'll say, let me move this for us here. All right, so the squared term on the left-hand side, watch this. The squared term on the left-hand side has a coefficient of 1. The coefficient of the squared term on the right-hand side has a coefficient of a plus b. So I'm going to equate the coefficients, those coefficients, because they have the same power. Squared term, squared term. So I'm going to say a plus b, this coefficient, must be equal to this coefficient. So I'm going to say a plus b is equal to 1, right? This second degree coefficient must be equal to this second degree coefficient. Let's try that again with the first degree terms. So the first degree term on the right-hand side is here, and the coefficient is b plus c. The first degree term on the left-hand side is here, 3x, and its coefficient is 3. So I'm going to say b plus c must be equal to 3. b plus c must be 3. Finally, I'll say this constant must be equal to this constant. So 2a plus c must be equal to -1. And what you have here is a system of equations. So if you solve this system of equations for a, b, and c using algebraic techniques from earlier studies in algebra, you can find those values of a, b, and c this way. Okay, so this is definitely another method that works, and it's really efficient. All right, last problem, everybody. 2x over x squared plus 1 squared times x minus 1. All right, a lot of stuff going on here. Here we go. Number one, step one. Notice that this is proper indeed. The numerator is degree 1, the denominator is degree 5, because x squared times x squared to the second power is x to the fourth. Then you got x to the first here, so it's degree 5. But anyway, it's proper. Step 2 is to factor your denominator, but it already is. X minus 1 is factored, x squared plus 1. Quantity squared is already factored as well. You cannot factor this any further, so that's good. So what we want to do is move to step 3, and we want to write this out as the following. Now notice that this here is a linear factor. This one's a quadratic factor, so it's just like the previous example, except this quadratic factor is being repeated. That did not happen in the previous example. So this example that we're concluding our lesson on has a repeated quadratic factor. So this is the first time we're seeing this, a repeated quadratic factor. So here we go. This must be written as the following. All right, so the first factor I'm going to use is this quadratic factor, x squared plus 1. And because that denominator there is quadratic, the numerator must be linear. So degree 1, so ax plus b. Now I have to account for the repeated quadratic factor, so x squared plus 1 squared. Now, because that there has a repeated quadratic factor, this also must be written as cx plus d. Okay, and then plus, now we're off to the linear factor, x minus 1. And let's see, going down your alphabet, A, B, C, D, let's call this E. All right, everybody? So these are written like this as linear numerators because you have quadratic factors. And then here, because this is a linear factor, this is just a constant. So as always, we're looking for what these constants are. We are looking for A, B, C, D, and E. We have 5 unknowns. What we're going to do here is the same thing that we've done for all of the examples now is we are going to multiply both sides by the LCD. Now the LCD is just simply this complete denominator. When you do so, you're left with just 2x on the left-hand side. But you're left with a whole lot on the right. All right, the right-hand side is ax plus b times x squared plus 1 times x minus 1. Plus cx plus d times x minus 1 plus e times x squared plus 1 quantity squared. Now, this is a lot, isn't it? So bear with me. Notice that what we can do right away is, notice that this term here contains a factor of x minus 1. And this term here also contains a factor of x minus 1. So if x were 1, then this factor would be 0, and this whole term would go to 0. And this factor would turn into 0 as well if x were 1, and then this whole term would go to 0, and you'll be left with just e. So we can find e relatively easily if we just let x be 1. So let's let x be 1. All right, I let x be 1, and it leads me to 2 is equal to 4e, which just gives me that e is 1/2. Awesome. So we're going to want to remember that all the way, until we get to the very end. All right, everybody? Don't forget that we found e to be 1/2. Now, what I'm going to do is I am going to go to our identity, which is right here, and I will update our identity with e being 1/2. Okay, I let e be 1/2. Now what I'm going to do, you ready for this? We will expand this. We'll distribute all of it, distribute this, and distribute all of this. Now be careful with your order of operations, especially here. You're going to want to square this binomial first and then distribute the 1/2. For this first one, it doesn't matter the order in which you multiply. I'm going to go ahead and, it's just a preference of mine, I'm going to distribute here first, and then when I'm done, I'll multiply by x plus b. All right, I'm doing this step by step here. And so I went ahead and distributed here and gave me x cubed minus x squared plus x minus 1. I distributed here and it gave me 6x squared minus cx plus dx minus d. And I squared this x squared plus 1 to give me x to the 4th power plus 2x squared plus 1. Now what I'll do is I will distribute ax here. Let me actually show you. I will distribute ax here. And then when I'm done, I will distribute the b like that. And then finally, I will, I shouldn't say finally because there's still a lot of work to do. I will distribute the 1/2 there. All right, let's see. So I went ahead and distributed. I got ax to the 4th power minus ax cubed plus ax squared minus ax plus bx cubed minus bx squared plus bx minus b plus cx squared minus cx plus dx minus d plus 1/2 x to the 4th plus x squared plus 1/2. Whew, it's a lot. Now, what we want to do is group like terms. So look at all of your quartic, your degree 4 terms. So let's see. Here's a quartic term. I'm gonna actually let me move the screen up a little bit, and I'm going to highlight. So you got a quartic term here, ax to the 4th, and you have a quartic term here, 1/2 x to the 4th. So what I want to do is I want to group those together. I also want to group the cubic terms together. So you got, I'm going to use colors here. You got negative ax cubed. You got positive bx cubed. Is that it? Yes, it is. I want to group those together. Let's go to second degree. Let's go to quadratic terms. So you got ax squared. You have negative bx squared. You have positive cx squared. And you have positive 1x squared. Now we're at first degree terms, and I don't know, okay, let's use green. We got negative ax, we got positive bx, negative cx, positive dx, and that's it for first degree terms. And I'm going to leave the constant terms just not circled, so that'll just pop, that'll be easy to see, hopefully. So what I end up having is, all right, I got it, folks. So I grouped all my quartic terms together, cubic, quadratic, linear, and constant terms together, all right? So what we're going to do at this point, as I move the screen up here, is we will endeavor to equate coefficients of like powers on each side, okay? We're going to equate the coefficients of like powers of x on each side. So, on the right side, I have degree 4, and the coefficients are a plus 1/2, a plus 1/2. So I get a plus 1/2 must be equal to the coefficients of degree 4 on the left-hand side. However, the left-hand side is just 2x. So where is the degree 4 term on the left-hand side? It's not there. Therefore, the coefficient of the quartic, the degree 4 term on the left-hand side, must be 0. So it's a plus 1/2 is equal to 0. That right there implies that a is equal to negative 1/2. We have one of our constants. Okay? Go ahead and box that if I can. All right. Let's go to the third degree terms. So I have negative a plus b, negative a plus b, negative a plus b must be equal to the coefficients of the third degree term on the left-hand side. However, the left-hand side doesn't have a third degree term, so that third degree term on the left-hand side must have a coefficient of 0. Okay, must have a coefficient of 0. Now, we already determined that a is negative 1/2. A is negative 1/2, right? So this would be negative 1/2. So this is now positive 1/2 plus b is 0, which then implies that b is negative 1/2 as well. So we know what a is, and we know what b is. Now, let's move to the cubic terms, okay? The cubic terms. So here, excuse me, that was a cubic term. Let's move to the quadratic terms, excuse me. So we have a minus b plus c plus 1, okay, is equal to the coefficients of the second degree coefficient on the left-hand side. Once again, the second degree term is not here on the left-hand side, therefore its coefficient must be 0. So then I'm going to say that a minus b plus c plus 1 must be 0. Now we've already determined that a is negative 1/2, b is also negative 1/2, so we can say, therefore, that c must be negative 1. Okay, c is negative 1. All right, so we're moving right along. We know a, b, and c. Now we need d, right? And don't forget, we found e already, right? In the very beginning, we found e to be, do you remember? E was 1/2. So there's only one constant left, which is d. So now let me actually, I'm off the screen. So let me come back here to the identity. Here we go. Now, excuse me, we're going to go to the first degree term, right, which is right here. Take this coefficient, negative a plus b minus c plus d. That coefficient must be equal to the coefficient of the first degree term on the left-hand side, which finally we have it. It's 2. So we're going to say this coefficient must be equal to 2. All right, now we found a already. A is negative 1/2, so this is negative 1/2. We found b to be negative 1/2 as well. And we found c to be negative 1. And we don't know what d is, right? So let's go ahead and figure out what d is now. Let's see, this here becomes positive 1/2. Positive 1/2 minus 1/2 is 0. So this is just positive 1. So then d will be equal to just 2 minus 1, which is just 1. So d is 1. All right, everybody, that was the last coefficient that we needed to find. And again, remember that we found e in the very beginning. E to be 1/2 in the very beginning. So let's go ahead and write out the partial fraction decomposition. All right, so here is the original expression here, and we found this to be the partial fraction decomposition. Excuse me for writing vertically here, just running out of space. So here is our coefficient of a, negative 1/2, our b is negative 1/2, our coefficient c is negative 1, d is positive 1, and e is positive 1/2. So now I'm going to ask you to rewrite all of this. So these denominators of 2 right here, the 2 will move down to the denominator. Okay, this is fine how it's written. This one here, I'll move this 2 down to the denominator as well. So I'm going to clean this up. All right, so much better. Here's the original expression, and then now we have a negative, excuse me, x plus 1 over 2 times x squared plus 1. So this 2 here used to be in the numerator. Well, it was in the denominator of the numerator, so now it's down here. Plus negative x plus 1 over x squared plus 1 quantity squared. We didn't make any changes to this middle partial fraction. And then plus, this 2 used to be the denominator of the numerator, so now we moved it down here, so we have 1 over 2 times x minus 1. So this is the partial fraction decomposition for this expression. All right, this concludes this lesson. It was, man, it was pretty dense. A lot of fun. I think it's a lot of fun trying to find the constants, and it's kind of like a mystery a little bit. So anyway, I hope you enjoyed it as well, and I'll catch you in a future lesson.